So let us start our discussion. We are going to start working on our neural network concepts today. So in neural networks, we are going to first discuss some basic concepts like optimization, and then we'll discuss some mathematics. So what are the concepts that we are going to see is your differential calculus. We are going to study maxima minima concepts. And then we are going to discuss what is stochastic gradient descent. And then we'll be talking about our artificial neural networks. So this is what we are going to see. So all these topics we'll be covering. And then we'll try to discuss with the help of some examples along the way. So now, so the most important topics what we have to focus on is optimization basics, our gradient descent method, and artificial neural network. In artificial neural network, we'll be talking about your feed-forward neural networks, multi-perceptron models, or we should call them as multi-layer perceptron model. And then we'll be focusing on your backward propagation concepts in our discussion. So all these topics we are going to see are feed-forward neural networks, multi-perceptron models, and multi-layer perceptron models, backward propagation concepts as part of our neural network discussion. Now, let us start with some basic concepts. What do you mean by optimization? So some examples are there here for optimization, based on which we can understand what is the logic. What do you mean by the concept called as optimization? The first example, what we are going to focus on is the example of US Federal Aviation Administration challenge. So US Federal Aviation Administration is responsible for air traffic management. Air traffic management. So what is the problem they are trying to understand first? So large scale weather systems or weather patterns reduce the available airspace for different aircrafts. So because of weather problems, they may cause some difficulty and they may reduce the available airspace for our aircraft. So we have to understand now the weather patterns. That is the problem what we have to work with. So we have to develop airspace flow programs which can understand your weather patterns, which can understand the airflow, and which can help us study the weather patterns. And what is the advantage when you are going to study your weather patterns? You can understand and you can reduce, you can optimize your ground delays. So you can help the aircraft in reducing the ground delay time in the available airspace, and you can reduce your costs. So what is it we are trying to do here? We are trying to optimize our ground delays for each individual aircraft when the weather pattern is not supporting us, when the weather pattern is difficult. So what is that we are trying to do? We are trying to optimize our ground delays for each and every individual aircraft. So what is the benefit because of this? The airline was able to save around $190 million in the first 2 years. So based on your optimization, you are able to reduce your costs. You are able to minimize your cost. So this is one form of optimization for us, minimizing our cost. This is the first example that we have. What is the second example? Second example that we are working with is Netherlands Railway Challenge. So we have to understand what is the problem statement first. So we have to develop a system which can optimize your 5,500 daily train routes. So we have to optimize our routes for our trains. That is the objective. So how many routes are there? 5,500 routes are there. And now how is this going to help us? If you optimize the routes, you can efficiently support your crew and rolling stock schedules. So the objective is to support our crew and rolling stock schedules, what we have in our trains. So what are the benefits if you actually develop this kind of system, which is going to optimize your daily train routes? You can improve your profit. You can improve your profit by 40 million euros. This is the potential what optimization can help us achieve. And it can also improve the on-time arrivals for our trains. It can improve on-time arrivals. So you can increase your profits, and also simultaneously you can also improve your on-time arrivals. So this can lead us to maximizing our revenue. So optimization can be a minimization problem for us, where you want to reduce your costs, where you want to save on expenses, or optimization can also be a maximization problem for us, where you want to increase your revenue, increase your profits. This can be the objective of your optimization. So this is what we are going to study. This is what we have to focus on when we are discussing the concept of optimization. Trying to minimize a variable, trying to maximize a variable, and find out what is the result. So a simple example can be to understand optimization. Suppose you have profit. So profit is a variable. It is a function of revenue and expenses for us. It is a function of revenue and expenses. So now you can either maximize your revenue to improve your profits, or you can minimize your expenses to improve your profits. So I want to study what kind of impact my revenue variable is going to have on my profits. I want to study what kind of variable my expenses is going to have on my profits. So what is the idea? If we try to simply change our input, how is it going to affect our output? If I change my revenue, how is it going to impact my profits? If I change my expenses, how is it going to impact my profits? This is what I want to understand. So this rate of change I want to understand. So what is the impact of my independent variable on my target variable? I want to study that. So how can I understand this rate of change? I can understand with the help of derivatives. So I can understand with the help of delta y by delta x. So a small change in input, delta x, a small change in my input, how can it affect my output? How can it impact my output? So I can study this using the concept of derivatives first. Delta y by delta x, or you can call it as dy by dx. So this is what I'm interested to find out. A small change in x, how is it going to impact my y? What kind of influence it is going to have on my target variable y? So what do you mean by delta y by delta x or dy by dx? It is nothing but slope. So if you go back to the concepts what we have discussed in mathematics in our 12th standard, dy by dx stands for slope. y2 minus y1 by x2 minus x1. This is the formula for calculating our slope. Now, if I give you a straight line like this, will we be in a position to find out what is the slope? Is it possible for us to find out what is the slope? It is very easy. What is the formula? Slope is equal to y2 minus y1 by x2 minus x1 plus. This is the slope. So your slope is minus 15 by 30 minus 0.5. It is a downward sloping straight line for us. It is a downward sloping straight line. So it is very straightforward for us to find out the slope of a straight line equation. Simply use dy by dx or y2 minus y1 by x2 minus x1 formula. Now, what if I give you a curve? What is that you are going to do? If I give you a curve like this, you have a curve. Now, you have to find out what is the slope at this point. What is the slope for my curve at this point you want to find out. So what is that you are going to do? Draw a tangent at this point. Draw a tangent at that point. Now when you draw a tangent at that point, consider a small area or neighborhood around that point. Consider a small area or neighborhood around this point. If you zoom into your image, and if you select a small neighborhood around this tangent point, say suppose you are considering a small neighborhood, a small region. Now what is that you can do? Once you have identified the small region, small neighborhood for us, you can apply the formula of y2 minus y1 and x2 minus x1, and you can find out the slope of your curve at that point. So this is what we are supposed to do. Slope of the line can be defined using the formula of dy by dx or y2 minus y1 by x2 minus x1, or change in y by change in x. This is how you are supposed to find out for a curve. So draw a tangent and then zoom into the point at which your tangent is touching the curve. And then select a small neighborhood around that point. And then you are supposed to find out what is the possible slope for your curve at that point. So why this is important? Why are we trying to understand? Because we want to study the impact of delta x on delta y. We want to study what is the impact of delta x on delta y. A small change in our input, how is it going to affect our output? That is what we are interested to find. That is our object. So now, that small change can be very, very small. That small change can be very, very small value for us. For example, that small change can be to the tune of 0.01, or that small change can be to the tune of 0.001, or that small change could be tune of 0.0001. So however small is that change, I still want to understand what is the impact on my target variable. I want to study what is the impact on my y. That is my focus. That is what I want to do. So even though that small change can be very, very small for us, but still I want to find out how is it going to impact my target variable y. So we don't know exactly what is that small difference, but still you want to find out. However small it is, we want to use that smallest of smallest differences, and we want to understand what is the impact on your target variable going to be. We want to study that. So what is the starting point for us? We have to understand some preliminary concepts in derivatives first. We have to understand some preliminary concepts in derivatives, because we are interested to study the concept of delta y by delta x, or we are interested to study the concept of dy by dx. So if I give you a simple equation like this, y is equal to x square, what is the shape of this equation going to be? Upward shaping parabola for us. This is going to be the shape of your equation. This is just an example what we are trying to understand here. Y is equal to x square for us. Now, if you want to find out what is the derivative of this equation, how will you find out delta y by delta x? Let us try to use the concept of first principles. If you have studied differential calculus in your 11th standard, you would have started off by studying the concept of first principles of derivatives. So we are going to use that, and we'll try to find out what is delta y by delta x. So y is equal to x square. This is the equation of your curve that you have. And now let us produce some small change in x. So x plus delta x. This is a small change what you are producing in x. So this small change is going to cause a small change in y for us. You can call that as dy or delta y. You can call that as dy or delta y. Anything is fine for us. So dy plus y is equal to x plus dx whole square. Now when you expand this, x square plus dx whole square plus 2x dx, you are expanding this. So what is happening? Your dx itself is very small change what you are introducing in your x. Your dx itself is very small change. What about dx whole square? Dx whole square is even more smaller than dx. So what can you conclude now? Because it is very, very small for us. Because it is very, very small, you can simply ignore this term. You can ignore your dx whole square term. This is what you're supposed to do. Now, write down our equation. Dy plus y is equal to x square plus 2x dx. Now, what is y? Y is x square for us. So dy plus x square is equal to x square plus 2x dx. So instead of y, I am substituting it as x square. X square are going to get cancelled, and I'll be left with dy is equal to 2x dx, and dy by dx is equal to 2x. So this is the derivative of our equation y is equal to x square. This is the derivative. dy by dx is equal to 2x for us. So this is what I have got. So I have derived this using the first principle of derivatives for us. So what is that we can conclude? The ratio of growing y by growing x is found to be 2x. The ratio of delta y by delta x is 2x. The ratio of growing y by growing x is 2x for us. This is what you can conclude. Now, if I want to use any formula, in your 11th standard, we would have discussed some formulas in derivatives. We have to remember those formulas. For example, one such formula, what you would have discussed in school, was power rule in derivatives. What is power rule formula? D by dx of x power n can be written as n into x power n minus 1. This is called as power rule. So d by dx of x square can be written as 2 into x power 2 minus 1. What is the value? 2x. So derivative of x square should be 2x. This is the answer what we got. Using the first principle of derivatives also, we got this as our answer. Similarly, there is another example for us. F of x is equal to x power 4. Then what is f dash x? You can write this as 4 into x power 4 minus 1. This is 4x cubed for us. This is the differential of x power 4. Suppose if I give you another example, y is equal to x power 8. Then how can you write this as 8 into x power 8 minus 1? I can write this as 8x power 7. So this is how I can use the concept of power rule, and I can find out the derivative of my equations. Of my curves, I can find out. What is another important formula, what you can remember? It is called as constant multiple rule for us. One is power rule, another is constant multiple rule. So how is your constant multiple rule going to work? D by dx of cu. C is constant. So what is that you can do? You can take the c outside of your derivative, and simply you can take the derivative of u. So you can write this as c into du by dx. This is called as constant multiple rule for us. So what is the example? D by dx of c x power n can be written as, take the c outside, c into d by dx of x power n. What is x power n? Derivative n into x power n minus 1. So that is how you are supposed to apply the concept of constant multiple rule. So d by dx of 7x power 5, how can you write this? 7 into d by dx of x power 5. How can you write this? 7 into 5 into x power 5 minus 1. So 35 into x power 4. Or you can write this as 35x power 4. So this is the derivative of our equation 7x power 5. So that is how we have to revise our concepts. Before we discuss further topics, we have to understand the basics of derivatives first. So remember these two formulas, power rule and constant multiple rule first. Now, what if there is a question now? Find out the slope and equation of the tangent line to the curve. So we have to find out the slope and equation of your tangent line to the curve. Y is equal to 2x square plus 1. This is the curve that we have. And at point 1, 3. So how will you find out the slope of your curve? Take dy by dx. Take the derivative of your curve. So d by dx of 2x square plus 1. So d by dx of 2x square plus d by dx of 1. What is d by dx of 2x square? It is 4x. What is d by dx of 1? It is 0. Differential of constant will always be 0 for us. This is another concept what you can remember. D by dx of constant will always be 0 for us. So what is your differential of your curve y is equal to 2x square plus 1? It is 4x. Now you have to find out at 1 comma 3 what is the slope value. So slope is nothing but dy by dx. Now I want to find out my slope at point 1 comma 3. What is the value of x? X is 1. So what is the slope? M is equal to 4 into 1. It is 4. So slope of my tangent line or I should say slope at point 1 comma 3 is going to be 4 for us. Now what is your next objective? You have to find out what is the equation of your tangent line. What is the equation of your tangent line? What is the formula? When you have a point 1 comma 3 and when you have slope, what is the formula of your equation when you have a single point and slope? So if you go back to our 12th standard coordinate geometry, there you would have studied this formula. Y is equal to or y minus y1 is equal to m into x minus x1. So y minus y1 is equal to m into x minus x1. This is the equation for your tangent line with slope value is equal to 4 and point 1 comma 3. So what is that you are going to do? What is y1 here? Y minus 3 is equal to slope 4 into x minus 1. So y minus 3 is equal to 4x minus 4. Y minus 4x is equal to minus 1. This is the equation of your tangent line with slope m is equal to 4 and then at point 1 comma 3. So y minus 4x is equal to minus 1, or I can write this as y is equal to 4x minus 1. This is the equation of my tangent line. So all these formulas we have to remember. How do you find out the equation of your straight line when a single point is given and slope is given? Y minus y1 is equal to m into x minus x. Now, all these calculations, whatever we have done, we are going to see them on our slides. So y minus y1 is equal to m into x minus x. So y minus 3 is equal to 4 into x minus 1. Y minus 3 is equal to 4x minus 4 and y is equal to 4x minus 1. Or you can use another simple formula, y is equal to mx plus c. And then what is the value of y? Y is 3. What is the value of slope? 4 into 1. So 3 minus 4 is equal to c. What is the c value? Minus 1. So y is equal to 4x minus 1 is going to be the equation of your tangent line at point 1 comma 3. So this is what you are supposed to understand. So how can you represent this diagrammatically? How can you represent this concept? How is our curve going to look like? Y is equal to 2x square plus 1. This is how the curve is going to look. This is my origin. 1, 2, 3. 1, 2, 3. And now this is our tangent line in red color. So it is going to touch your curve at point 1 comma 3. So this tangent line is going to have the equation of y is equal to 4x minus 1 at this point 1 comma 3. What is the slope of your tangent line? M is equal to 4. So this is what you are supposed to understand. So we are just revising all the concepts, what we have studied in the past. Simply revising all the concepts. Now, There is another important derivatives concept. What we have to understand is chain rule of derivatives. It is called as chain rule of derivatives first. So what is chain rule? Dy by dx can be written as dy by dz into dz by dx. So I can cancel dz and dz. I'll be left with dy by dx. So simply you're transforming your dy by dx data in terms of dz. Simply transforming your dy by dx in terms of dz. So this is important rule what we are going to use in updating our weights. So there is a concept what we are going to study. It is called as back propagation. And there we are going to use this chain rule of derivatives and we are going to update our weights for all our input features, for all our inputs. And then using these updated weights, we are going to make our predictions. That is what we are going to do. That is what we are going to study. So keep this concept at the back of your mind. It is called as chain rule of derivatives for us. Dy by dx is equal to dy by dz into dz by dx. So you have your input layer. This is x, your input. You have your output. And then in between you have something called as z, or you can call it as hidden layer. So all these terms will become familiar once we discuss more concepts. Then all these terms will become familiar and you'll be able to understand what are the important topics. So remember this formula, chain rule of derivatives, dy by dx is equal to dy by dz into dz by dx. Now we have to study the concepts of maxima and minima. So far we have studied your differential calculus, slope, tangent, chain rule of derivatives. All these concepts we have discussed. Now we are going to focus on maxima and minima. So you have two diagrams here. So let us focus on the first diagram. So what can be the equation of this curve? It is a downward shaping parabola for us. So your equation can look like y is equal to minus x squared. So this can be the equation of your curve. Now what is it we have to understand when you're working with these kind of curves? Identify what is happening to the slope. The slope is changing from positive. So slope here is positive for us. And then it is changing from positive to negative. So when the slope of your curve is changing from positive to negative, what can you say? We can say that this kind of curve is going to have a maxima value. This curve is going to have a maxima for us when the slope is changing from positive to negative. What about this curve? What about your second diagram? What can you say? When the slope of your curve is changing from negative to positive, what is that you can say? What can be the equation of this curve? Y is equal to x square. It is an upward shaping parabola for us. So when my slope is changing from negative to positive, I can say that this kind of curve is going to have a minimum value, or it is going to have a minimum. So this is based on your slope change. When the slope is changing from negative to positive, what is that minimum value? This point is going to be that minimum value. So when the slope is changing from negative to positive, your curve is going to have a minimum. When the slope is changing from positive to negative, your curve is going to have a maxima. All these are important points. What we have to remember. Now, my next question is, how can we find out what is that minimum value the curve is going to have? How can we find out what is the maximum value that curve is going to have? How can we find out? What is happening to the slope here? At this point, what is happening to the slope? The slope is becoming 0 for my curve. So how are you going to find out the minimum value and maximum value for us? How are you going to find out? Simply find out the first differential of your curve and then equate it to 0. You will be in a position to find out what is the minimum value for your curve, what is the maximum value for your curve. So take your first differential for both your curves and then equate it to 0 to find out what is the minimum value, what is the maximum value. That is what we are going to do. So first, let us try to understand your curve. Y is equal to minus x square. If you take the first differential, what will happen? Dy by dx is equal to minus 2x. Equate this to 0. What is the value of x? 0. What is the value of y? 0. So this is the maximum value of your curve. This is the maximum value 0, 0 for your curve y is equal to minus x square. So this is going to be the maximum value. Or you can call it as your critical value. Or you can call it as critical points. So for your curve, y is equal to minus x square. This is going to be your critical value. Or it is going to be your critical point. This is the maximum value for your curve. 0, 0. That is what you have to understand. What about the minimum value for this curve? The same concept. Y is equal to x square. This is the equation of your curve. Take the differential. Dy by dx is equal to 2x. Then equate this to 0. X is 0, y is 0. So what is that you can understand? 0, 0 is the minimum value for this curve. 0, 0 is the minimum value for this curve. Or you can call this as critical points or critical values for your curve y is equal to x square. So that is how our job is to find out your critical points. What is the minimum value? What is the maximum value? We have to find out. That is the logic. Now, suppose you want to find out whether my curve is going to have maxima or my curve is going to have minima for us. If you want to find out whether your curve is going to have maxima or your curve is going to have a minimum, so use your first derivative test. Same concept what we have discussed, we are trying to experiment with a numerical example. That is what we are trying to understand here. So to find out whether the curve is going to have a maxima value or a minima value, you are going to apply the first derivative test. So what do you mean by first derivative test? Find out what are your critical values. Find out what are your critical points. How will you find out? Take the differential and equate it to 0. You will be able to find out what are your critical values. What are your critical points. Now around this critical point, you are going to consider some values, some data points you are going to consider. Suppose, for example, Around this critical point 0, you are considering -1 as one data point, 1 as your another data point. Now find out what is the slope at these points. Find out what is the slope at these points -1 and 1. So how will you find out? dy by dx is equal to minus x square, or I should say y is equal to minus x square. Then dy by dx is equal to minus 2x. So what is the slope at this point -1? It is -2. What is the slope at this point 1? It is 2. So what is that we are trying to do? We are trying to find out the slope at point -1. What is the slope at point -1? 2. What is the slope at point 1? It is -2. So this is what we are getting. Now, how is your slope changing? Your slope is changing from negative, or I should say positive to negative. What is happening? Your slope is changing from positive to negative. So whenever your slope is changing from positive to negative, what is that you are going to conclude? The curve is going to have a maxima value. This is what you are going to conclude. Same thing you do here. Find out what is the critical point. 0, 0. Then consider two data points around this neighbor, -1 and 1. So find out what is the slope at point -1. What is the slope at point 1? What is the slope at -1? It is -2. What is the slope at 1? It is 2. So what is happening to your slope? Slope is changing from negative to positive, -2 to +2. When the slope is changing from negative to positive, you can say that the curve is going to have a minimum value. This is what you're supposed to say. The curve is going to have a minimum value first. So when the slope is changing from -2 to +2, the curve is going to have a minimum value. When the slope is changing from positive to negative, +2 to -2, what is that you are going to change? You are going to say that the curve is going to have a maximum value. This is called as first derivative test for us. This concept is called as first derivative test. Now, you can also find out whether the curve is going to have a maxima or a minima value using the concept what all of us are familiar with. What is the concept? Using second derivative test. Using second derivative test, you can find out whether the curve is going to have a maxima value or minima value. First, find out whether the second derivative is positive or not. So y is equal to x square. Imagine this is the curve. Dy by dx is equal to 2x. D square y by dx square is 2. This is the second derivative. So second derivative is positive. If my second derivative is positive, then what is that I'm going to conclude? The curve is going to have a minima value. The curve is going to have a minima value. It is going to look a parabola which is upward shaping, or you can call it as concave up. This structure is called as concave up, or you can call it as an upward shaping parabola. So if your second derivative is positive for us, then you can say the curve is going to have a minimum value. What about this curve? Y is equal to -x square. Dy by dx is equal to -2x. D square y by dx square is -2. So second derivative is less than 0. What is that you can say? The curve is going to have a maxima first. it is going to look like this. It is a downward shaping parabola, or you can say it is concave down. The structure is called as concave down. So by heart these points. If your second derivative is negative, then your curve is going to have a maximum value. It is going to look like a downward shaping parabola or concave down. If your second derivative is positive, then your curve is going to have an upward shaping parabola structure, or you can call it as concave up, and your curve is going to have a minimum value. That is what you are supposed to understand. This is the concept of maxima and minima for us. Same concept. You can see them on our slides. So take the second differential. If your second differential is less than 0, you can say the curve is going to have a maxima value. And if your second differential is positive for us, you can say the curve is going to have a minima value. So upward shaping parabola and downward shaping parabola, or you can call them as concave up, concave down. Now, to summarize all our calculations, what we have done. So first, you have the equation of your curve. Then you're trying to find out the first differential of that equation equal to 0. And you can solve for your critical points or critical values. Then if you want to find out whether the curve is going to have a maxima value or a minima value, what is that you can do? You can simply use the first derivative test. If the slope is changing from positive to negative, it is going to have a maximum value. If the slope is changing from negative to positive, it is going to have a minimum value for us. So you can either use your first derivative test or your second derivative test to find out your curve is going to have a maxima value or minima value for us. So all these points you can write down, you can remember. Now some examples are there for us to understand. So simple example is there, y is equal to x square minus 3x plus 2. This is the equation of our curve. So what is that you're supposed to do? Take the first differential, 2x minus 3 equal to 0. You're going to get your critical point. And then take the second derivative test. Second derivative test is positive for us. And then therefore you can say the curve is going to have a minima. That is the logic. So all these examples you can solve and you can understand the concept. You can take a look at your 12th class mathematics textbook, where you are going to have a lot of examples for maxima and minima concepts. Why these concepts are important for us? Because we are going to apply them in our stochastic gradient descent algorithm. Or for now, I'm supposed to say only gradient descent algorithm. Later on, I'm going to use that word. For now, focus on gradient descent algorithm first. So this is where we are going to use the concept of maxima and minima for us. So imagine you are working on a linear regression problem. Imagine we are working on a linear regression problem. And our job is to fit a best equation which can pass through all our observations on our data set and which can minimize the error. So this is our line of best fit, what we are trying to fit on our data set. And these are your actual values. What is this vertical distance? This vertical distance is called as error. Vertical distance is called as error. What is the formula for your error? It is the difference between your predicted value and actual value. It is the difference between your predicted value and actual value. Now, what is our objective? We have to minimize our error. So what is the most common error metric that we can use? in your regression problems, we can work with your residual sum of squares, or you can call it as error sum of squares. So our objective is to minimize your residual sum of squares. Our objective is to minimize your error sum of squares. That is what we are supposed to do in order to fit our line of best fit, in order to fit our best equation on our data set. So this I can call it as my error function, what I can consider. Now I have to minimize my residual sum of squares or error sum of squares. That is the objective. So how can I do this? I'm going to apply the concept of gradient descent algorithm. I'm going to apply this. So what is your gradient descent algorithm for us? It is an iterative optimization algorithm used in machine learning. It is an iterative optimization algorithm used in machine learning to get the best results. Best results of what? Best results for your parameters. Best results for your coefficients, or you can call them as weights. So if this is your curve, what is your objective? Your objective is to minimize your residual sum of squares. At this point, you are able to ensure that your error is minimized. So at this point, you're supposed to find out what are your parameter values. What are your values for slope and intercept? So at that point, you're supposed to find out what are the values for your slope and intercept. And these values are going to be considered as the best values for my equation, which can minimize my error to 0. So what is that we are going to do? We are going to start experimenting from the top of your curve with different values for slope and intercept. And then as we keep changing our slope and intercept values along the curve, we will be able to slowly come up with most suitable equations for your data set. And finally, at this point, when you reach this minimum value, you can ensure that at this minimum value, you are going to find the best equation for your data set, which can minimize your residual sum of squares to 0. And you will be able to find out what are those optimal values for your slope and intercept. So it is the gradient descent algorithm. Descent means descending. So we have to keep moving in the downward direction. We have to keep descending to the bottom of your curve till you find out the best values for your slope and intercept. That is what you are going to do. So the algorithm is iterative, means we need to get results multiple times to get the most optimal result. So now when I play the animation, you will be able to understand what is this concept. I'm going to play the animation. So what is happening when we change the slope at every point? What is happening? You are able to slowly understand what is the best equation. Finally, at this minimum value, you see, you are able to get the best equation for your data set. So that is what you have to do. You have to keep experimenting with different values of slope and intercept. And at this minimum value, you are going to fit the line of best equation on our data set. That is what is our object. So that is what you're supposed to do. So this algorithm is called as gradient descent algorithm first. So that is what you are going to do. So We can take a break here for 10 minutes and then we can come back after 10 minutes to continue our discussion on gradient descent algorithm first. So take a break for 10 minutes. So let us continue our discussion. So gradient descent method. So what is the basic idea that we are trying to understand here? We have an objective function. This is your objective function for us. And you can call it as your cost function. We have to minimize our objective function. So this objective function W is a vector of multiple variables. So it is a vector of multiple variables that you have. So you can have multiple variables. It can be your slope, your intercept, and you can have different coefficients in your equation. So we have to iteratively minimize your cost function by finding the gradient of the function surface. You have to minimize the cost function by finding the gradient. This is called as the function surface. So you have to find out the gradient of your function surface. Now function surface is what? Function surface is nothing but it is the variable space. So our job is to understand each and every variable that you have in the variable space, and you have to differentiate your overall cost function with each and every variable that you have in the variable space. Then you are going to find out how each and every variable is influencing our cost function. How each and every variable in our variable space is actually impacting our cost function. We can understand when you actually find out the gradient of this function surface. That is what you are going to do. So this gradient is nothing but it is a vector with each element representing the slope of your function. With each vector, all these are different vectors that I have. Each vector is going to represent the slope of your cost function or your objective function in the direction of one of your variables, in the direction of your variable slope, in the direction of your variable intercept, in the direction of your coefficients. That is what this gradient vector is trying to represent us. Each element in this gradient vector is a partial derivative of the function with respect to one of the variables. So each element is a partial derivative of the function for us, partial derivative of our cost function with respect to one of the variables. So if this is our curve, this is our different weight values, and this is our cost function or error function. So we have to start from some point on the top and we have to approach this minimum value. Sometimes what may happen, you may exceed this minimum value and you may reach somewhere here. So what you're supposed to do then, you have to simply move in the opposite direction. You have to move in the opposite direction because you have exceeded this minimum value, right? Minimum point. So you have to move in the reverse direction. And this is the point at which you are going to get your most optimal weight values or most optimal values for your parameters. So that is what you are going to do. That is what you are supposed to do. We are supposed to find out what are the most optimal values for our parameters or our weights or our coefficients. And you have to use them in our equation to reduce your residual sum of squares. That is what is our objective. So we have an example here. We have a quadratic function in two variables, x1 square plus x1 x2 plus 3x2 square. So x1, x2. This is our cost function that we have. And now what is it you're trying to do? You're trying to minimize your residual sum of squares. So starting from somewhere at the top of your quadratic function, somewhere at the top, then you have to slowly minimize in the descending order. And then at this point, you will be in a position to minimize your cost function. And at this point, you are going to get the most optimal values for our x1 and x2. This is what you are going to do. So you have to find the minimum value for our curve. So how will you find out the minimum value for our curve? Simply take the differential. Take the differential and equate it to 0. So at this point, your slope of your curve is going to become equal to 0. So take the gradient of your function surface. Take the gradient of your quadratic function and equate it to 0. That is when you are going to get your most optimal values for your x1 and x2, which can reduce your residual sum of squares to 0. Which can reduce your error sum of squares to 0. That is what you are going to do. So this is your cost function. F of x is equal to x1 square plus x1 x2 plus 3x2 square. So now this function has to be differentiated with respect to x1 and x2. So you are going to take the partial derivative. Because you want to study only the impact of x1 on your quadratic function. You want to study only the impact of x2 on your quadratic function. That is what is the area of focus. So take the partial derivative with respect to x1. You are going to get 2x1 plus x2. Take the partial derivative of your equation with respect to x2. You are going to get x1 plus 6x2. So then you can solve. You can equate this value to 0 and you can solve for your x1, x2 values. And those values are going to be the most optimal values, the best values for us. Which can reduce your residual sum of squares to 0. That is what is our objective. That is what we have to find out. So basically trying to find out the minimum values for your curve. That is what we are trying to do here. So this is our quadratic function that we have. F of x1, x2. Then differentiate with respect to your x1, x2. Find out your most suitable values. Find out your most suitable values for x1 and x2. That is what you are going to do. So you have to move in the opposite direction. Of your variables. You have to move in the reverse direction because you have to find the minimum value. That is what you're supposed to do. Now, what is the pseudocode? How can you write the pseudocode for your gradient descent algorithm? That is the question. So now we have the error function. First, define your error function or your cost function. It is nothing but it is a gradient vector with all our weights, with all our coefficients, or you can say parameters. It is a function of all our weights. Now, what is that we are going to do? We are going to start with initial set of weights. We are going to start from the top of our curve. We are going to start from here and we are going to select some random weights. We are going to select some random weight values, W0, W1, and so on, WD. That is what we are going to do. And we are going to move in the downward direction because we have to reach the minimum value, right? So you have to move in the downward direction. And when you are moving in the downward direction, what is going to be the slope? The slope is going to be negative for us. Slope is going to be negative. And then we have to choose something called as learning rate. Learning rate is nothing but it is a hyperparameter for us, which can control what fraction of rate of change of slope I want to consider for updating my weights. So it can control what fraction of learning I want to consider for updating my weights. That is called as learning rate for us. So now imagine there is some learning rate hyperparameter. Now W new weight is going to be W old weight minus learning rate into your rate of change of slope. This is the formula, what you are going to use to update your weights. So you have to keep on updating your weight values. You have to keep on experimenting with your different values of your coefficients or parameters. And then at this point, when you reach the minimum value here, what is it you're going to do? You have to stop updating your weights. Because you have to stop updating your weights, you have to stop experimenting with different values, because this is going to give you the least error for your function. So at this point of time, what is it you're going to do? What is the stopping criteria? How do you know when you have reached the bottom of your curve? You can understand when the slope of your curve is going to become equal to 0. You can understand that you have reached this minimum point. When your slope becomes equal to 0, you can understand that you are reaching, or you have reached the minimum value of your curve. So when your rate of change of your slope for your weights is getting close to 0, or it has become 0 for us, then at that point you can understand that you have reached the minimum point of your curve. So what will happen when your slope is 0? When your slope is 0, when this value is 0 for us, then you are no longer in a position to update your weights. So you can no longer update your weights at your minimum point of your curve. That is when you have to stop. So those are your best values for your weights, and you can use them in your equation and make your predictions. It is going to give you the best result for us. So this is how you have to develop the pseudocode for your gradient descent algorithm, gradient descent method for us. Now, diagrammatically, how can we understand? We have to start from somewhere at the top. And initially, you are going to start with some random values. So initially, you are going to start with some random values for W1 and W0. And our job is to minimize your error. So error function is always a function of your weights. It is a function of your coefficient. It is a function of your parameters. So initially, you are going to start with your random values. This is going to be your W0. This is going to be your W1. These are your random weights, what you are going to start with. Now, slowly you have to move in the downward direction. Slowly we have to move in the downward direction for us. So you're updating your weights. Initially, you started off with these values, but now what is happening? You are updating your weights. You're slowly able to update your weights, and you're able to slowly reduce your error, reduce your residual sum of squares. That is what is our objective. That is what you're supposed to do. So this is the idea about your gradient descent optimization method, so that you find this minimum point on your curve. That is what is your target. Now, what are some challenges that you can face along the way? What are some problems that you are going to face? It is very difficult for us to estimate what should be the learning rate for our gradient descent model. So if you select a too small learning rate, what will happen if you select a too small learning rate? It will take forever to reach this minimum value. It will take forever. What is the problem if you select too large learning rate? it may not ever converge. It may not ever converge first. It will keep bouncing off around that minimum value, and it may not ever reach that minimum value of our curve. So you should be very careful when you're deciding the value of your learning rate. It should not be very, very small. It should not be very, very large first. And the another challenge is it can get stuck on the flat areas. So suppose if you're starting from here, from the top of your curve, and there is a possibility that it can get stuck in these flat areas. So what are these flat areas called as? They are called as plateau region, plateau. So what will happen in the plateau region? Plateau region, it will assume that the slope is 0. And then you will not be in a position to update your weights. When you're not in a position to update your weights, what will happen? You are no longer in a position to reduce your residual sum of squares, or you're no longer in a position to reduce your. So that is a challenge what you're going to face. It can get stuck in these flat areas. These flat areas are called as local minima. So it should not get stuck in this local minima. It should find the global minima. And then it should quickly reach that global minima and give us the most optimal solution for our equation. That is what is the objective. So some challenges are there. We are going to discuss what are the possible solutions in a few minutes. How can you overcome these problems? So gradient descent is a generic optimization algorithm capable of finding optimal solutions to a wide range of problems. So gradient descent is to tweak parameters iteratively. So we have to keep tweaking our parameters iteratively, tweak our weights in order to minimize our cost function. That is the idea. That is the overall objective of your gradient descent method. Now, in gradient descent method, we have different variants of gradient descent. Under gradient descent method only, we have different variants of gradient descent method. What are they? We'll try to understand with the help of one example. So you have your data set here. And then my X variable is number of years of experience that I have. And Y is salary. So based on number of years of experience, what is the salary that I can get? That is the question. And you have all these data points. All these data points are there for you. Now, this is the equation that you can develop. We are trying to work out with a linear regression equation for our data set. These are your weights, theta naught and theta 1. And this is what you have to predict. What is the salary with your experience? Now define first what is your loss function or error function you define. So error function for your linear regression problem can be your residual sum of squares. So take the difference of your error. Take the difference of your predicted value and actual value. This is error. Take the square of your error and then take the summation of your errors. So this is residual sum of squares. But now why do we have 8 here? Because we are considering your mean square error. So after taking the squared errors, take the average. So you're dividing by number of observations that you have in your data set, 8. And what is this 2 here? 2 is nothing but for mathematical convenience. I'm just including 2 there. Because when I take the differential of x squared to x, this 2 and this 2 can get cancelled. That is the reason why I'm considering my loss function in this manner. So I can generalize my loss function like this. So it is a function of your weights, theta naught and theta. Now, what is our objective? We have to understand the concepts of different variants of gradient descent with the help of this example. We have to understand what are the different variants of gradient descent that I have with the help of this example. So this is the data set that I have. Now, the first variant of gradient descent is called as batch gradient descent. So batch gradient descent is nothing but you are going to consider all the observations in your data for updating your weights. So in each iteration, you are going to consider the entire data set for updating your weights. That is one variant of gradient descent. It is called as batch gradient descent. Then you have stochastic gradient descent. Stochastic gradient descent is nothing but you are going to use only one observation. So one observation in every iteration you are going to use separately, and for every observation you are going to update your weights. For every iteration you are going to consider one observation and you are going to update our weights. This is called as stochastic gradient descent. Then you have mini batch gradient descent. What is mini batch gradient descent? You are not going to consider the entire data set, nor you are going to consider single observation, but you are going to consider somewhere in between. Maybe you can consider 2 observations or 3 observations or 4 observations every iteration and update our weights. So any of these 3 different variants of gradient descent you can use. It is up to your choice. Any of these 3 variants you can use. Now, what is that we are going to do? It is that time of the day. So let me share you the attendance link. Just give me 1 minute. I've just shared the attendance link with you. So please use this link and try to fill in your details. And then you can always come back and you can listen to our sessions. So try to fill in your attendance sheet, go to this link, and you can always come back and listen to our sessions. Let us do that first. So we are here. We are trying to understand our different variants of gradient descent. So the first variant what we have seen is batch gradient descent, when you are going to use the entire data set for updating your weights in each iteration. Then a stochastic gradient descent, where you are going to use every single observation to update our weights. And then mini batch gradient descent, we are not going to consider the entire data set, nor we are going to consider every single observation for updating our weights, but somewhere in between, maybe 2 or 3 or 4 observations. So this is how our cost function is what we have defined. This is what we have defined our loss function or cost function. Now take the differential. So theta new is equal to theta old minus learning rate into j dash of theta. This is the formula for updating our weights. This is what we are supposed to do. So we have to find out what is j dash of theta. So find out what is j dash of theta. When you take the differential, you are going to get this value as your j dash of theta. That is the value what you are going to get. J dash of theta. Now, attendance link has been shared. Sai Kiran. I'm pasting it again. Go to the attendance link. Fill in your details. Tell me if that link is working or not. So first we are going to study batch gradient descent. So in batch gradient descent, what is your objective? You have to consider all your observations in your data. All your observations you are going to consider, entire data. So now theta new is equal to theta old minus n into learning rate into j dash of theta. So consider all your observations. Consider all your data points for updating your weight. So this is called as batch gradient descent for us. Batch gradient descent. What about your stochastic gradient descent? What is it you are going to do? You are going to only consider one observation. That is what you are going to see. You are only going to consider one observation. And then you are going to update your weights. This is called as stochastic gradient descent. So simply, when you are programming this logic in Python, you can say batch size is equal to 1. When you say batch size is equal to 1, you are only considering one observation. And therefore, it becomes a stochastic gradient descent model, what you are trying to build. It is going to become an example of your stochastic gradient descent model. That is what you can do. Now, attendance link has already been shared here. Can you see T. Srinivas? It has already been pasted here. Try to go to that link. Yes. Now, mini batch gradient descent. What is mini batch gradient descent? You are not going to consider the entire data set. You are not going to consider a single observation, but somewhere in between. So you can take maybe 2 observations. You can take maybe 2 observations. For example, you can do this. So randomly select 2 observations. So I can say batch size is equal to 2. Then automatically you can understand that whatever model that we are building, it is using the concept of mini batch gradient descent. So you are going to use your 2 observations. For updating our weights. Now, my question is, among these 3 variants of gradient descent, which one is better for us? Among these 3 different gradient descent algorithms, if you compare stochastic gradient descent, what is happening? There is too much of confusion for us. Why there is too much of confusion? Because every single observation, you are updating your weight. You are updating your weight. So there is too much of confusion here. You have to reach this point, but there is too much of confusion. What is happening? You are not settling down here. You are not settling down. at the minimum. That is the problem what you are going to face with your stochastic gradient descent. What about batch gradient descent? Batch gradient descent will take longer time for convergence. Will take longer time for convergence or reaching your minimum point. It will take longer time for reaching the minimum point. So which is the best option that we have? So the best option that we have is mini batch gradient descent. So this is the best variant option what you can use when you are building your neural network models. That is the idea. Mini batch gradient descent. On YouTube. Okay. Let me just try once. Give me one moment. Okay, probably one of you can maybe copy paste the link. Just try to copy paste the link what I'm sharing with you with the YouTube audience and help them out. If one of you can take the initiative and do that, it will be of great help for me. Just try to copy paste the attendance link there. Yeah, thank you very much. Yeah. So now, what is the best gradient descent variant we have? It is mini batch gradient descent. So keep this concept at the back of your mind. And then we are going to apply these concepts. Mini batch gradient descent. Okay. Just 1 second. Okay, yes. Soon the link will be shared in YouTube also. No worries for us. Now, linear regression example. This is what we are going to consider. So imagine you have our equation y is equal to mx plus b. This is the equation that we have. Yeah, sure. Attendance link will be shared in few minutes on YouTube. So no worries. Meanwhile, you can listen to our lecture. Y is equal to mx plus b is the equation what you are supposed to fit on your data set. This is what you are supposed to do. Now, first, what is that you are going to do? You have to define your error function. You have to define your loss function. That is what you are supposed to do. So define your loss function. Error function I have defined. Now after that, I am going to run my gradient descent algorithm. So what is that I am going to do? I have to run my gradient descent algorithm. So we will have to start from somewhere, some location on the top, and we will have to reach the bottom. So somewhere on the top, we have to start and move downhill to find the line with the lowest error. We have to reach this minimum value, which can give us the lowest error or lowest residual sum of squares. That is what is our objective. That is what we are going to do. Now, so start. So start with some random values for slope. M is equal to -1, B is equal to 0. M is equal to -1 and B is equal to 0. I'm starting with some random values for my parameters. So then this is my first set of random values. So for M is equal to -1, B is equal to 0, my equation is completely incorrect. My equation is completely wrong. It is underfitting my data. It is underfitting my data. So what I'm going to do, I have to keep on experimenting using my gradient descent algorithm. I have to keep on experimenting with different values for my slope and intercept. So let us try to experiment. So when you change your value now, M has become 0.40, B has become 0.18 for us. Then what is going to happen? At least now I'm able to understand what is the direction of my data. This model is better than the previous model what I got. So like this, you have to keep on iterating with different values of your slope and intercept first. So how many times you are going to iterate this? You are going to iterate 2000 times. After 2000 times, you have got your final values. M is equal to 1, intercept is equal to 3.07. You have got your slope value and intercept value. Now what is that you are going to do? After 2000 iterations, you can understand that this is the line of best fit. This is the best equation for our data set. This is the best equation for our data set. Okay, that is what we are going to do. Attendance link, I'm going to share it again. So no worries, people who are not able to fill in their attendance form today, we'll try to share it in your Telegram group. Okay, we'll do that. So all of you can accordingly fill in the attendance form for today. So no worries. So try to follow our concept. What is it we are doing? We are trying to experiment with different values of slope and intercept first in every iteration. So after every iteration, what is happening? You are improving your slope and intercept values. So because of this improvement, you are able to reduce the error. So after iterating for many times, after iterating for 2000 times, what is that we are able to conclude? We are able to reduce our error to 0. A good way to ensure that gradient descent is working correctly is to make sure that error decreases after each iteration. So a good way to ensure that your gradient descent is working is to understand that after every iteration, your error is decreasing first. So that is how you can figure out that the gradient descent algorithm is working, because your error is decreasing after every iteration. You're slowly trying to get to your optimal values. That is what you have to understand. So that is the concept of your gradient descent algorithm. So now, try to remember all the topics that we have discussed, all the concepts. Try to remember so far what we have discussed, because they are important. They will help you understand the next topic what we are going to discuss. Your neural networks. Under this, we are going to discuss artificial neural network first. Under which we are going to discuss artificial neural network first. So artificial neural network is nothing but it models the relationship between a set of input signals and output signal. It models the relationship between a bunch of input signals and your output signal. So just like how your brain uses interconnected cells called as neurons to establish a relationship between your input and output. Your artificial neural network also uses something called as artificial neurons to establish the relationship between your input and output. So artificial neural network will use a network of neurons first. A network of neurons. That is what you have to keep in mind. So these neurons will establish a relationship between your input and output. That is important for us. Now, the human brain, for instance, is made up of approximately 80 to 100 billion neurons. It is made up of 80 to 100 billion neurons. Then this network is capable of representing tremendous amount of knowledge. Just 1 second. So human brain is made up of 80 to 100 billion neurons, resulting in a network capable of representing tremendous amount of knowledge. So more the number of neurons you have, more is the knowledge. Then what about cat? Cat has roughly 750 million neurons. So this is also a very interesting fact what we have. Similarly, mouse. Mouse has about 75 million neurons first. It has 75 million neurons. And similarly, cockroach has about 1 million neurons. So this is what we have to understand. So more the number of neurons, the more complicated is our network and the more amount of knowledge your network is capable of. That is what we have to understand here. So that is very important for us. So going forward, we are going to work on these concepts. We are going to discuss how can we establish a mathematical equation for our neuron. How can we build a neural network with the help of neurons? How can we transmit information from one neuron to another? All these concepts we'll be discussing as we proceed forward. And we are also going to touch upon some topics like feed-forward neural networks, backward propagation, and then we are going to discuss our hyperparameters. So today we have seen one hyperparameter, learning rate first. So batch size also you can say it is one form of your hyperparameter. You can decide what should be your batch size. So there are multiple hyperparameters what you can use when you are working on your neural network concepts. So all these topics we are going to discuss going forward in our next session. That is the idea. So today, what are the concepts that we have discussed? We started off with optimization. Optimization can be minimization or it can be maximization for us. And then we discussed the concept of slope, your differential calculus. And remember, we have seen two formulas. One is power rule. One is constant multiple rule that we have seen. And then also remember your chain rule of derivatives. Remember chain rule of derivatives for us. dy by dx can be written as dy by dz into dz by dx. This is important chain rule what we are going to see in updation of our weights when we are working on the concept of backward propagation. And then what are the other topics that we have discussed? We have seen maxima, minima concepts. So remember all the examples that we have seen in maxima, minima. What do you mean by critical points? So simply equate your differential to 0 and you can find out your critical points. And then find out whether the curve is going to have your maxima or minima using the first derivative test. Or you can use your second derivative test. So all these things, try to remember these concepts. That is the idea what you're supposed to have. And then finally our stochastic gradient descent, or I should say a gradient descent. What are the different variants of gradient descent? One is stochastic, one is batch gradient descent, another is mini batch gradient descent. So revise all these concepts. And tomorrow, there is no class for us. Your next class will be on Monday. So Monday, we are going to follow up with our discussion on neural networks. And we will try to implement them in our Python Jupyter notebooks. So with that, take care, everyone. Thanks for your time. And I'll see you all again on Monday. All the best.